They said I was insane, that I was wasting time and money digging a hole that would accomplish nothing, that I clearly didn't understand how things worked in rural Alaska, where the ground freezes solid and stays that way for 8 months of the year. My name is David Kowalski. I'm a 44-year-old geothermal engineer, and in 2019, I moved to a small town called Willow, about 70 miles north of Anchorage, Alaska. I'd spent 15 years working for energy companies in the lower 48, designing geothermal systems for commercial buildings, understanding heat transfer and ground temperatures and how to extract energy from the earth itself. But I'd never applied that knowledge to residential construction, never built something for myself, never tested my theories in the extreme conditions of interior Alaska. I bought 5 acres of land with a small, dilapidated cabin that the previous owner had abandoned after one brutal winter. The cabin was maybe 600 square feet, poorly insulated, sitting on a basic pier foundation that left a 2-foot crawl space between the floor and the frozen ground. The heating system consisted of an oil-burning furnace that consumed fuel at an alarming rate while barely keeping the interior above freezing. The previous owner's heating bills had reportedly run over $600 per month during winter for 600 square feet. That's $1 per square foot per month, an absolutely unsustainable cost that had driven him to abandon the property entirely. My neighbors, the few hardy souls who lived year-round in this remote area, thought I was foolish for buying the place. They warned me that heating costs would bankrupt me, that the cabin was too small and poorly built to be comfortable, that I'd end up abandoning it just like the previous owner. But I had a plan based on 15 years of professional experience and a deep understanding of geothermal principles that most people, even in the engineering community, didn't fully grasp. The plan was simple in concept, but complex in execution. I was going to dig beneath the cabin, excavate the crawl space down to a depth where ground temperatures remained constant year-round, and create a geothermal buffer zone that would precondition air before it entered the cabin's heating system. In Alaska, ground temperatures 6 feet below the surface remain at approximately 32 to 35 degrees Fahrenheit year-round, regardless of whether the surface temperature is 70 degrees in summer or -40 in winter. That constant temperature, while cold by human comfort standards, is dramatically warmer than winter air temperatures and could be used to significantly reduce heating loads. But I wasn't going to stop at 6 feet. I was going to dig down 12 feet, creating a massive thermal mass zone beneath the cabin that would store heat during the brief summer months and release it slowly during the long winter. I was going to install a network of air circulation tubes that would pull outside air through this underground zone, pre-warming it from negative temperatures to above freezing before it entered the cabin. And I was going to insulate the entire system so thoroughly that heat loss would be minimal, creating a thermal battery that would dramatically reduce my heating costs while keeping my floors warm instead of ice cold. My neighbors thought I'd lost my mind. When I started excavation in June 2019, using a small excavator I'd rented, they gathered to watch and offer commentary. Most of it was negative. "You're digging under your cabin," said Tom Brennan, my closest neighbor about a half-mile away. "You know the ground is permafrost, right? You can't just dig down 12 feet. You'll hit ice and rock. And even if you could dig that deep, what's the point? Cold air sinks. You're just going to make your floor colder, not warmer." I tried to explain the principles of geothermal heat exchange, of how ground temperatures remained constant below the frost line, of how I could use that constant temperature as a baseline to precondition air and reduce heating loads. But Tom wasn't interested in theory. He'd lived in Alaska for 30 years, had built his own cabin using traditional methods, and he knew what worked and what didn't. And digging a giant hole under your cabin definitely didn't work, in his opinion. His wife Sarah was more direct. "You're an engineer, right?" she said. "Book smart but no common sense. This is Alaska. We heat with oil or wood or propane. We insulate the hell out of everything. We don't dig holes and expect the ground to heat our homes. The ground is frozen solid. It can't give you heat because it doesn't have any heat to give." I didn't argue. I just kept digging. The excavation took 3 weeks of hard labor. The ground wasn't permafrost, despite Tom's assertion. Willow was just south of the permafrost zone, and while the ground froze solid in winter, it thawed in summer, allowing me to dig. I excavated beneath the cabin's footprint, going down 12 feet, creating a space that was roughly 600 square feet in area and 12 feet deep, approximately 7,200 cubic feet of volume. I shored up the cabin's support posts, ensuring the structure remained stable while I worked beneath it. I removed tons of soil, piling it nearby for later use. And I created a massive underground chamber that would become the heart of my heating system. The neighbors watched with a mixture of fascination and pity. They were certain I was wasting my time and money, certain that this crazy scheme would fail, certain that I'd end up with a flooded basement and a collapsed cabin and a very expensive lesson about why you don't mess with Alaska's frozen ground. But I wasn't done. The excavation was just the first step. Next came the infrastructure that would make the system work. I installed a network of perforated drainage pipes at the bottom of the excavation, creating a system that would prevent water accumulation while allowing air circulation. I built a series of vertical air tubes, 6-inch diameter PVC pipes that extended from the surface down to the bottom of the chamber, creating pathways for air to enter the system. I installed horizontal distribution pipes that would spread air throughout the underground space, maximizing contact with the thermal mass. Then came the insulation, and this is where my engineering background really mattered. I lined the walls of the excavation with 6 inches of closed-cell foam insulation, creating a thermal barrier that would prevent heat exchange with the surrounding soil. I wanted the underground chamber to be thermally isolated, to maintain its own temperature independent of the frozen ground around it. This seemed counterintuitive to my neighbors, who couldn't understand why I'd insulate an underground space. "You're trying to get heat from the ground," Tom said, watching me install foam panels. "Why are you insulating it? You're blocking the heat transfer you're trying to achieve. You're making it worse, not better." I explained that I wasn't trying to extract heat from the surrounding ground. I was trying to create a stable thermal mass that would store heat from summer and release it in winter, and that required insulation to prevent that stored heat from dissipating into the frozen soil. But Tom just shook his head and walked away, convinced I didn't know what I was doing. After the insulation came the thermal mass itself. I filled the underground chamber with a carefully calculated mixture of materials designed to store heat. I used crushed rock, approximately 400 tons of it, creating a massive heat sink with high thermal mass and good air permeability. I added water in controlled amounts, filling the voids between rocks, increasing the thermal mass even further. Water has one of the highest heat capacities of any common material, meaning it can store enormous amounts of energy with relatively small temperature changes. The combination of rock and water created a thermal battery with a heat storage capacity of approximately 2.5 million BTUs per degree Fahrenheit of temperature change. That meant if I could raise the temperature of this mass by just 10 degrees during summer, it would store 25 million BTUs of energy that could be released during winter. For context, heating my 600 square foot cabin for an entire Alaska winter required approximately 40-50 million BTUs, meaning this thermal mass could potentially provide half my heating needs just from stored summer heat. The final component was the air circulation system. I installed a small, energy-efficient fan at the surface that would pull outside air through the vertical intake tubes, force it through the underground chamber where it would be warmed by contact with the thermal mass, and then deliver it to the cabin's crawl space directly beneath the floor. The warmed air would heat the floor from below, and any excess heat would rise into the cabin's living space. The entire system was designed to operate continuously at very low flow rates, providing steady, consistent heating rather than the on-off cycling of conventional furnaces. By September 2019, the system was complete. I'd spent approximately $8,000 on materials, excavator rental, and the specialized components I'd needed. I'd invested 3 months of hard physical labor, working alone most of the time, occasionally hiring help for the heaviest tasks. And I'd created something that, as far as I knew, had never been built before. A deep geothermal thermal mass system designed specifically for extreme cold climates. My neighbors were skeptical but curious. They'd watched me build this elaborate underground system, and now they wanted to see if it would actually work, or if I just wasted time and money on an expensive hole in the ground. The test would come with winter, when temperatures dropped and heating demands soared. I spent September and October charging the thermal mass, running the circulation system to pull warm summer and fall air through the underground chamber, storing heat in the rock and water mass. Surface temperatures in September averaged 50-60 degrees, and I was pulling that air through the system, warming the thermal mass from its baseline 32-35 degrees up to approximately 45-50 degrees. Every degree of temperature increase represented millions of BTUs of stored energy. By November, when temperatures started dropping below freezing consistently, I'd stored a significant amount of heat in the underground mass. Now came the real test. Would that stored heat be enough to make a difference? Would the system work as I'd calculated, or had I made some fundamental error in my assumptions? The first serious cold snap came in mid-November, with temperatures dropping to 10 degrees Fahrenheit. I turned on the circulation system, pulling outside air through the underground chamber and monitoring temperatures at various points in the system. The results were immediate and dramatic. Outside air at 10 degrees entered the system through the intake tubes. As it passed through the underground chamber, making contact with the warm thermal mass, it was heated to approximately 38 degrees, a 28-degree temperature increase with no energy input other than the small fan. That 38-degree air was then delivered to the crawl space beneath my cabin floor, warming the floor itself and providing a baseline heat that my conventional heating system could build upon. The impact on my heating costs was significant. My oil furnace, which would normally have been running constantly to maintain comfortable temperatures, was now only supplementing the geothermal preheating. My floor, which in a typical Alaska cabin would have been ice cold, requiring thick insulation and rugs to be tolerable, was now relatively warm, approximately 28 degrees warmer than it would have been without the system. The comfort difference was remarkable. Walking barefoot on my floor was actually pleasant, something that would have been impossible in a conventional cabin. The entire living space felt warmer, more comfortable, more livable. And my heating costs, which I'd been told would run $600 per month or more, were running approximately $200 per month, a 67% reduction. I was vindicated. The system worked exactly as I'd calculated it would. But I didn't tell my neighbors right away. I wanted to see how it performed through the entire winter, through the coldest months of December and January, when temperatures would drop to -20 or colder, when the real test of the system would come. December 2019 brought the kind of cold that defines Alaska winters. Temperatures dropped to -15, then -20, then on one particularly brutal night, -32 degrees Fahrenheit. This was the real test of my geothermal system, the conditions that would prove whether my calculations were correct or whether I'd built an expensive failure. I monitored the system obsessively during those cold weeks, taking temperature readings at multiple points, measuring airflow rates, calculating heat transfer and energy consumption. The data was remarkable and exceeded even my optimistic projections. When outside temperatures dropped to -20 degrees, my system was pulling that frigid air through the underground thermal mass and delivering it to my crawl space at approximately 35 degrees, a 55-degree temperature increase. When temperatures hit -32, the system was still delivering air at 32 to 34 degrees, a temperature increase of 64 to 66 degrees. The thermal mass was performing exactly as designed, storing enough heat from the fall charging period to maintain above freezing temperatures, even when outside air was dangerously cold. The impact on my cabin was transformative. My floors remained warm, not hot, but genuinely warm to the touch, approximately 60-65 degrees even when outside temperatures were -20. The crawl space beneath the cabin, which in a conventional structure would have been a source of cold air infiltration and heat loss, was now a source of warmth, a buffer zone that preheated air before it entered the living space. My oil furnace was running maybe 30% of the time it would have run without the geothermal system, and my heating costs for December were $180, less than a third of what the previous owner had reportedly spent. But the real revelation was the comfort. Living in a small Alaska cabin during winter is typically an exercise in managing discomfort. You're constantly aware of the cold, constantly adjusting layers of clothing, constantly seeking the warm spots near the heat source, while avoiding the cold spots near windows and exterior walls. My cabin was different. The floor radiated gentle warmth. The temperature was even throughout the space. There were no cold drafts, no ice-cold spots, no constant awareness of fighting against the cold. It was genuinely comfortable in a way that Alaska cabins typically aren't. By late December, my neighbors had noticed something unusual. They'd seen smoke from my chimney, indicating I was home and presumably heating the cabin, but they weren't seeing the constant plume of exhaust from an oil furnace running continuously. Tom Brennan stopped by on a day when temperatures were hovering around -10, ostensibly to borrow a tool but really to investigate. I invited him in, and I saw his expression change the moment he stepped through the door. "Your cabin is warm," he said, looking around with confusion. "Actually warm. And your floor?" He bent down and touched the floor with his bare hand. "Your floor is warm. How is that possible? It's -10 outside. Your floor should be ice cold." I explained the system, walking him through the principles of geothermal heat exchange, thermal mass storage, and air preconditioning. I showed him my temperature logs, the data demonstrating that the underground chamber was consistently delivering air 50–60 degrees warmer than outside temperatures. I showed him my heating bills, proving that the system was reducing costs by 2/3 while improving comfort. Tom listened, examined the data, and finally admitted something I hadn't expected. "I was wrong," he said simply. "I thought you were crazy, thought you were wasting time and money on something that couldn't possibly work. But this is incredible. You're heating your cabin with the ground, with stored summer heat, with physics instead of just burning fuel. This is the most efficient system I've ever seen." Word spread quickly in our small community. Sarah Brennan came by the next day, felt my warm floors, saw my low heating bills, and immediately wanted to know if the system could be retrofitted to their cabin. Other neighbors stopped by, curious about the underground chamber that was apparently defying Alaska's brutal cold. The local newspaper sent a reporter, and I ended up giving an interview about geothermal principles and thermal mass storage and how ancient techniques could be combined with modern engineering to create highly efficient systems. The article attracted attention beyond our small community. I started getting calls from people across Alaska, from builders and homeowners who were struggling with heating costs, from engineers who were intrigued by the concept, from researchers at the University of Alaska who wanted to study the system and understand its performance characteristics. In January 2020, the coldest month of the year, my system faced its ultimate test. We had a week where temperatures didn't rise above -20, with several nights dropping to -35 or colder. These were the conditions that broke conventional heating systems, that drove heating costs to astronomical levels, that made Alaska living genuinely difficult. My system continued to perform. The thermal mass, despite months of releasing stored heat, still maintained enough energy to pre-warm incoming air by 50 to 55 degrees. My floors stayed warm. My heating costs for January were $220, and my cabin remained comfortable even during the coldest weather. I'd proven the concept beyond any doubt. By February 2020, I'd been approached by a local builder who wanted to partner with me to offer geothermal thermal mass systems as an option for new construction. He'd seen the performance data, understood the economics, and recognized that this could be a game changer for Alaska housing. We formed a partnership, with me providing the engineering design and him handling the construction. Our first collaborative project was a new cabin for a young couple who were building on a remote lot about 20 miles from Willow. They'd heard about my system and wanted something similar but larger, designed for a 1,200 square foot home. I scaled up the design, creating an underground chamber that was 1,200 square feet in area and 14 feet deep, with proportionally more thermal mass and more sophisticated air circulation. The excavation and construction took 6 weeks in summer 2020, and the total cost was approximately $18,000, which seemed expensive until you calculated the heating cost savings. The clients were heating a 1,200 square foot home in interior Alaska for approximately $300 per month during the coldest months, compared to the $800 or $1,000 they would have spent with conventional heating. The system would pay for itself in saved heating costs within 3 to 4 years, and would continue saving money for decades after that. But more importantly, their home was comfortable in ways that conventional Alaska homes weren't. Warm floors, even temperatures, no cold drafts, no constant battle against the cold. They could walk barefoot in January, could sit anywhere in the house and be comfortable, could actually enjoy winter instead of just enduring it. We completed 3 more projects in 2020, each one a custom design tailored to the specific site and building. Each one performed beautifully, delivering 50-60 degree temperature increases in incoming air, dramatically reducing heating costs, and providing comfort that exceeded anything conventional systems could achieve. By 2021, we had a waiting list of clients who wanted geothermal thermal mass systems. The economics were compelling, the comfort was undeniable, and word was spreading throughout Alaska's building community that there was a better way to heat homes in extreme cold climates. Tom Brennan, who'd been my most vocal skeptic, became one of my biggest advocates. He retrofitted his own cabin with a smaller version of the system, digging beneath his existing structure and installing thermal mass and air circulation. His heating costs dropped by 50%, and his floors went from ice cold to pleasantly warm. He started telling everyone he knew about the system, about how he'd been wrong to dismiss it, about how this was the future of Alaska housing. The University of Alaska Fairbanks sent researchers to study my original system, installing monitoring equipment and collecting data on performance throughout the heating season. Their findings confirmed what I'd been documenting. The system was delivering consistent 50-60 degree temperature increases in incoming air, was storing and releasing approximately 20-25 million BTUs of energy per heating season, and was reducing heating costs by 60-70% compared to conventional systems. They published a paper in a renewable energy journal, and suddenly I was getting calls from across the country, from cold climate regions in Montana, Minnesota, Maine, even Canada, from people who wanted to understand the principles and potentially implement similar systems. The concept wasn't limited to Alaska. Anywhere with cold winters and significant heating demands could benefit from geothermal thermal mass storage. The key was understanding the principles, doing the calculations correctly, and building systems that were properly sized and insulated for the specific climate and building. By 2022, 3 years after I'd built my original system, I'd designed or consulted on over 30 geothermal thermal mass installations across Alaska and other cold climate regions. Each one was unique, tailored to specific conditions, but they all shared common principles that I'd refined through experience and data collection. The science behind the system was actually quite simple, though the implementation required careful engineering. The key insight was understanding that ground temperatures below the frost line remain constant year-round, and that this constant temperature, while cold by human standards, is dramatically warmer than winter air temperatures in cold climates. In Alaska, ground temperatures 6 feet below the surface are approximately 32-35 degrees year-round. In Montana, they're 40-45 degrees. In Minnesota, 45-50 degrees. These temperatures are cold, but they're 50-80 degrees warmer than winter air temperatures in these regions. By pulling outside air through an underground chamber filled with thermal mass, you can pre-warm that air from dangerously cold temperatures to above freezing temperatures with no energy input other than a small circulation fan. But the real innovation in my system was the addition of seasonal thermal storage. By charging the thermal mass during summer and fall, pulling warm air through the system when it was available, I could raise the temperature of the underground mass significantly above the baseline ground temperature. In my original system, I'd raised the thermal mass from 32 to 35 degrees to approximately 50 degrees by the end of fall, storing millions of BTUs of energy that would be released slowly throughout winter. This seasonal storage was the key to achieving 50-60 degree temperature increases in incoming air, far beyond what would be possible with just the baseline ground temperature. The economics were compelling and became more so as I refined the designs and reduced costs. A typical residential geothermal thermal mass system costs $12,000, $25,000 to install, depending on size and site conditions. But it would reduce heating costs by 60 to 70%, meaning it paid for itself in 4 to 7 years in Alaska, faster in regions with higher fuel costs. After payback, it was pure savings, year after year, for the life of the system, which could easily be 50-plus years with minimal maintenance. But beyond the economics, there was the comfort factor that was harder to quantify, but deeply valued by everyone who lived with these systems. Warm floors in winter were a luxury that transformed how people experienced their homes. Even temperature distribution eliminated hot and cold spots. Reduced air infiltration improved indoor air quality. The gentle, consistent heating was more comfortable than the on-off cycling of conventional furnaces. Multiple clients told me that the geothermal system had changed how they felt about winter, had made their homes feel like sanctuaries instead of just shelters, had improved their quality of life in ways that went beyond just saving money on heating bills. The University of Alaska research had broader implications beyond just residential heating. The principles of seasonal thermal storage could be applied to commercial buildings, greenhouses, even infrastructure like roads and runways where frost heaving was a constant problem. The researchers were exploring applications I hadn't considered, using thermal mass storage to prevent permafrost thaw, to extend growing seasons in cold climates, to reduce the energy demands of buildings in extreme environments. By 2023, the building codes in Alaska had been updated to include provisions for geothermal thermal mass systems, recognizing them as a legitimate and effective heating strategy. This was significant because it meant builders could offer these systems without navigating regulatory uncertainty, and homeowners could get financing and insurance without complications. The code changes were directly influenced by the performance data from my systems and the University of Alaska research. My neighbors, who'd thought I was insane for digging a giant hole under my cabin, were now asking me to design systems for their properties. Tom and Sarah Brennan had become close friends, and we'd collaborated on several projects together. The skepticism that had greeted my original project had transformed into enthusiasm and advocacy, with people throughout the region recognizing that this was a better way to build in cold climates. The local builder I'd partnered with had made geothermal thermal mass systems a standard offering, and approximately 30% of his new construction projects now incorporated the technology. He'd trained his crew on installation techniques, had developed efficient construction methods that reduced costs, and had become an expert in his own right on thermal mass design and implementation. In winter 2023-2024, my fourth winter with the system, I had the opportunity to directly compare performance with a neighbor who'd built a new, conventionally heated cabin of similar size. His cabin was well built by Alaska standards, with good insulation and an efficient propane furnace. My cabin was older, smaller, and had the geothermal system. During January 2024, when temperatures averaged -15 degrees, his heating costs were $520 for the month. Mine were $160. His floors were cold, requiring thick rugs and slippers. Mine were warm enough to walk on barefoot. His cabin had noticeable temperature variations, with cold spots near windows and warm spots near the furnace. Mine had even temperatures throughout. The comparison was stark and undeniable. The geothermal thermal mass system wasn't just marginally better than conventional heating. It was dramatically better, providing superior comfort at a fraction of the cost. And the gap would only widen over time as fuel costs increased while the geothermal system's operating costs remained minimal. By spring 2024, 5 years after I'd started digging that hole beneath my cabin, I'd consulted on over 60 installations across Alaska and other cold climate states. I'd trained other engineers in the design principles, had published technical papers explaining the calculations and methodologies, had given presentations at building science conferences. The concept that had seemed crazy to my neighbors in 2019 was now recognized as innovative and effective. A genuine advancement in cold climate building technology. The financial impact was significant. Homeowners with geothermal thermal mass systems were saving $3,000 to $6,000 per year on heating costs compared to conventional systems. Over a 20-year period, that was $60,000 to $120,000 in savings, far exceeding the installation cost and providing genuine economic benefit to families living in expensive-to-heat regions. But the broader impact was about changing how we thought about heating and building in cold climates. For decades, the approach had been to build insulated boxes and pump heat into them using fossil fuels, fighting against the cold through brute force energy consumption. The geothermal thermal mass approach was different. It worked with natural systems, using the Earth's constant temperature as a baseline, storing summer heat for winter use, preconditioning air before it entered living spaces. It was more elegant, more efficient, and more sustainable than conventional approaches. Tom Brennan, who'd been my harshest critic, summarized the transformation well in a conversation we had in spring 2024. When you started digging that hole, "I thought you'd lost your mind," he said. "I couldn't understand why anyone would excavate beneath their cabin, why you'd spend money and time on something that seemed so crazy. But you understood something I didn't. You understood that the ground isn't just frozen dirt. It's a thermal resource, a battery that can store and release heat, a buffer against temperature extremes. You saw potential where I just saw permafrost. I learned something important from watching your project. I learned that sometimes the crazy ideas are the ones worth pursuing, that innovation often looks ridiculous until it works, and that expertise and education matter. You're an engineer. You understood heat transfer and thermal dynamics in ways I never could, and that knowledge let you build something that actually works better than anything we'd been doing for decades. My neighbors couldn't believe what I built under my cabin. They thought it was a waste of time and money, a crazy scheme that would never work. But then winter came, and my floors stayed 28 degrees warmer than theirs, and my heating bills were a third of what they were paying, and suddenly the crazy idea didn't seem so crazy anymore. That's the story of the geothermal thermal mass system that changed cold climate building, and the lesson about innovation, persistence, and the value of understanding physics instead of just following conventional wisdom. Sometimes the best solutions are literally right beneath our feet, waiting for someone with the knowledge and courage to dig deep enough to find them.